So as we start the unit, not the unit, the chapter, there's technically chapters 4, 5, and 6 all somewhat have to do with trigonometry. 6 is kind of mostly with triangles and like application-y things, law of cosines, law of sines, that sort of stuff. Geometry. Hey, that's not bad. Some of you might be like getting ready for an ACT, SAT something. It's not totally bad for that stuff. If you haven't noticed, SAT is starting to include unit circling things like sine, cosine.
Why?
Just because. But in a way, it should be a good thing because a lot of kids that are taking the SAT are probably in classes like Algebra 2 and Precalc, and so it's something they're actually learning currently as opposed to learned a long time ago. If you think about it.
Let's not have it.
Just not the SATs? Boycott? Okay. I understand. I don't totally agree with how dependent college acceptances are on SATs and financial aid, but it's the way the world turns. Okay, so standard position of an angle, but not just any angle. We're not talking about like bless you. Anytime you measure an angle, there has to be a little XY plane, but we're talking right now specifically about angles in XY planes, coordinate axes, okay? If you're putting an angle in an XY plane, or if you're even doing physics and there's something like, I don't know, an incline or something like that, there's like a little trailer that's going up the incline, hey, that's a thing. If you're trying to measure the angle, you could think of it as a little XY plane. Now, is there an XY plane in the sky or on the ground, or no? There's not. We can still think of it and then think about the angle as being measured up from it, right? So anyway, in order to get ready for practical applications, let's talk about angles and XY planes. A few things about standard position of an angle. First of all, the vertex of the angle. What's the vertex of an angle? Do you remember? Yeah, the point where the two lines meet. We always put the vertex of an angle at the point 0, 0, hence at the origin, right? As much as is possible, an angle in standard position has to have the vertex of the angle at 0, 0. You measure, or if you rotate counterclockwise, it's going to be a positive angle. AKA when you rotate counterclockwise, you're rotating positively, you're measuring the angle positively, therefore let's just go ahead and say this angle as you rotate counterclockwise, theta would be greater than 0, it would be a positive number. Ooh, theta. That's Greek. Letter C, if you're measuring clockwise, what kind of angle is that going to be?
Negative.
Yep. There are different times as to when each should be helpful, etc. But the theta down here will be less than 0 because you're rotating the other direction. Really quickly before we go too much further, what quadrant is this one right here? Quadrant 1. What's true in quadrant 1 as far as x's and y's?
Positive, positive.
Positive, positive, right? So we have x greater than 0, y greater than 0. What quadrant is this?
2.
Let's just say what's x? Positive or negative?
Negative.
Y, because you're going to the left, right? So x is negative and y is positive, because to get to any point in the second quadrant, you go left and you go up. So x is negative, y is positive. Quadrant 3?
Negative, negative.
Negative, negative, because you go left and down. So x is negative, y is negative. This isn't really trig, this is more just graphing points, right? Kind of. Thinking about the Cartesian plane, the coordinate axes, the xy plane, whatever you want to call it. Last but not least, quadrant 4. You're going to the right, good. X is positive, and you're going down, y is negative. Good? And at the very bottom of the page, angles are frequently named with Greek letters. Now, why would we need more than one Greek letter to name an angle? Why not just call them all theta? Yeah, it's kind of the same reason why we have different variables, x, y, z, p, e, r, t, I, a, b, whatever. I was trying to use some of those ones from the last chapter and the different models. But We have different variables because we have different quantities or different things. And so with angles, well, we might have different angles. And we could just name them all like theta 1, theta 2, theta 3, theta 4. But that gets boring and it gets complicated when you're labeling a graph. So it might be useful to have some more Greek letters than just theta. Remember, theta is like a little O with a horizontal line through it, not a vertical. That could get a little messy if you start doing that. But there are some other Greek letters, whoa, that you could use. Only write down the ones that are highlighted. If you want to practice your Greek alphabet, you just go for it.
Pi is a Greek letter.
Yes. Just the highlighted ones. Why? We're not going to use all of them in pre-calculus, but some of them show up in other classes too. Alpha and omega, well, that's religion. Just it's in the Bible. You guys don't really see the Greek letters, though. You just read the words. Lambda. What? Mu? Gamma. Oh my goodness. This is science now, right? No? No gamma rays? Why are there two different ones? No. Capital and lowercase. Capital's on the left, lowercase is on the right. Pi is actually a tall pi, but he's not very curly. He's more linear. Yeah, sigma's fun. We'll use him with sequences and series in chapter 11. Phi photon. Alpha, beta, gamma, delta. Epsilon. Zeta, eta, theta. Iota, kappa, lambda, mu. This is not just so that you know what to avoid in college. Two reactions, I'll take it. So they're going to come up in science, they're going to come up in chem, they're going to come up in math, they're going to come up in physics, they're going to come up in electrical engineering if you go that route. They're going to come up in Bible. Yeah, it's like a W, but kind of like squished at the top. What? Yeah, don't even comment. They show you where not to join. You guys know how to make a sigma, right?
Yeah.
Just do a little curly, whoosh, and then you do. That's what I do anyway. I guess you do the whole like.
I do sigma.
What do we have to be careful of with this one right here?
Who
is he not?
Theta.
Okay, he's not theta, that's true. But I mean, vertical and horizontal, theoretically, we should be okay with that. But what in math could we maybe confuse him for?
0. Oh, not equal to.
Who's that?
Not 0. Not equal to.
Kinda.
Not 0.
Something called the empty set. Empty set means no solution. Yeah, no solution. It doesn't work. Kind of like undefined, does not exist. They ask you for something, you put that, and you're like, there is nothing. Now, usually, now we use nastier things like DNE or undefined, but back in the day, I think it was probably geometry, maybe algebra 1. You had to have learned an empty set, because you might have forgotten.
Oh, no.
Alpha, I don't really like this lowercase alpha very much. It's not horrible. I don't like the lowercase one much. Usually you see a little bit more like that. But either way. Are we good? Going, and okay. Last year, did you learn something about radians? In geometry, did you learn something about radians?
No.
Oh, come on. You've seen radians before. But that doesn't mean that necessarily you have a good understanding as to who a radian is and why it's different than a degree. We're more used to degrees. How come? This little instrument you worked with a long time ago called a protractor. Protractors are built with what? Or are marked by units of what? Degrees. 45 degrees. Oh yeah, 90 degrees. 135. Hopefully you can get that one. 180. Hopefully we have that one too. Degrees, we have a quick, hopefully, somewhat quick natural understanding of because of all of our work in geometry, and maybe in Algebra 2 a little bit, and Algebra 1 just a little bit. But radians, well, they were a lot newer. They probably didn't even come up. Maybe in geometry some. Should have been Algebra 2 more. So I'm going to try and help you get even a better grasp. But in order to do so, I have to start with the formula. The formula is an angle measured in radians. And that's very specific because, as you know, hopefully, angles can be measured in radians or degrees, right? There is a formula that says an angle measured in radians is equal to S, which, hopefully looking at the picture, you're like, oh, hey, I know what S is. It's the measure of the arc, aka the arc length. Now here's geometry. Divided by the radius. An angle measured in radians is equal to the arc length divided by the radius. So it's a ratio. And the crazy thing about ratios is if you have something like, I don't know, if this was measured in miles and you had 10 miles over 5 miles, that'd be 2 miles, right? Oh wait, miles would cancel, you just have 2. Or if you had 10 centimeters over, what did I say, 5 centimeters? You would still have 2. It doesn't matter how big the circle is. With radians, it can be a huge circle, it can be a tiny circle, but either way, the ratio ends up being the same number. Whether it's in miles, whether it's in centimeters, whether it's in millimeters, whether it's in, I don't know, anything in between. The ratio ends up being the exact same for a certain location, and the units end up canceling. Radians are dimensionless. Degrees, not so much. Now, are you guys used to seeing what this one down below shows?
No.
Like going up to here is 1 radian and 2 radians and 3 radians and 4 radians and 5 and 6. Oh, it doesn't even stop. It doesn't even go all the way. I apologize. It doesn't even go all the way around. Give me a second. Let me expand on that just a little bit. But yes, I do want you to copy it. But why is it messy? The numbers are nice. 1, 2, 3, 4, 5, 6. No big deal, right? But what's messy about this picture? The numbers are nice, 1, 2, 3, 4, 5, 6. But what's not nice?
Where the numbers are.
Where they are. Because there's 1, there's 2, there's 3, but well, who wants to deal with that awkward angle? I would rather deal with the one that's 180, right? So 3 isn't enough to make 180. Oh. And then I have 4, and then I have 5, and then I have 6. That doesn't even close the circle. So even though the numbers are nice, they don't help me with the circle itself because it doesn't get a semicircle, it doesn't get a whole circle, so there must be decimal radians. And there are decimal radians. You guys know at least one of them because it comes from an old formula called the circumference formula. The old circumference formula says C equals pi over D, right? Or it could be 2 pi over R. Question. If you take the entire distance around the circle, hey, isn't that an arc length? If you take the entire distance around the circle divided by a radius, what would perfectly measure the entire circle? Circumference is the arc length of the entire circle divided by radius. Hey, that's my formula. Where does 2 pi being a whole circle come from? Oh. It comes from this relationship of what is a radian. Now, the crazy thing is, 2 pi, there is no unit. If it was degrees, there'd be a little degree mark. In radians, it's kind of like a little understood radian. Why am I saying understood? I don't know. You guys have taken English for a while now, right? If I say, go to the store, what's the subject of that sentence? Ooh, grammar.
Go to you.
The understood you. But I didn't say you. But I meant you. It's understood, right? Same thing here. If I say 2 pi, I'm talking about an angle and there's no degree mark. What should be understood? Okay. So degree marks, they're given, they're shown, they're there. They're like little subjects to sentences that you do say. I'm going to the store. You go to the store. He goes to the store. Blah, blah, blah. Okay. Those are like degree marks. But when you just say 2 pi, there's no little degree mark. There's an understood radian. Now, let's say this one other way. Ready? What if I was to take something like, what do I have that's circular? Why am I getting something flexible like a string? Hold on, arc length. Can I just measure with a ruler arc length? No, why not? Because it's curved, right? So I'm not going to get a ruler for arc length. I need something curved. That's why maybe some of your moms have a flexible measuring tape if they do any sewing. No? Okay, never mind. But anyway, people used to sew. So coming back. We need something flexible, right? So I can measure around, so I can measure the arc length. It's not going to be perfect. I'm going to approximate. Hold on a minute. I have a circle up here, right? So if I wanted to approximate pi, let's say, I don't know, this is like thousands of years ago, and I'm like, I wonder if there's a ratio that seems to correspond with. People were measuring around circles and were measuring across circles and realizing there was a special number that seemed to keep on coming. So I'm kind of measuring around, I'm kind of doing linear pieces, so it's not going to be perfect. Doing an approximation. Of course, this could be way more precise to say it was an actual object and I can make it nice and tight. It'd probably be easier to measure all the way around instead of only halfway around. Almost there. Let's go a little bit more. Okay. All right. Let's do centimeters because it's a little bit more precise, right? Someone in your calculator, help me out really quickly. I want you to. Aw, he's too long. Okay, hold on. Let's do 30. Okay. Let's say 33. Okay, 33. That was the distance of the arc. That was the distance of the arc of the half circle, right? Okay. What if I was to now measure, so I'm doing the angle of the half circle. Now I measure across and I end up with, about there. What did I say, 33?
Yeah.
Okay, perfect. 33 divided by, let's say, 10.8. What do you guys get? Oh. Now, was there a little bit of error in that? If I had done that perfectly, what would the ratio have been? 3.1415926 because I did a half circle, and a half circle is how many radians? Pi. Now, how is, and this is 0, or 2 pi if I keep going around, how is this different than degrees? How many degrees does it take to get a half circle?
180.
Is 180 equal to 3.1415926? No. But kind of. It depends on the units. Here's a question. Is 12 equal to 1?
No.
But isn't 12 inches 1 foot? Oh. Right? Is 10 equal to 1?
No. In the metric system.
In the metric system, if I'm talking about millimeters and centimeters, right? Is 60 equal to 1?
No.
Unless I'm talking about 60 minutes and 1 hour. Ooh, is 5,280 equal to 1? Not unless I'm talking about feet and miles. I'm talking about bridges, aren't I? Am I talking about units? Am I talking about dimensional analysis a little bit? No. So, really quickly, are radians and degrees different? Yes. How? Degrees are little baby tick marks, and we'll write down a few notes on degrees. Little baby tick marks that you guys have learned just to be able to relate really quickly with. 90 degrees, you're like, yay, 180, yay, 45, got it, 30, 60, and these other ones in between. Radians are harder. Why? Because basically, we have to imagine a ruler. We have to imagine a ruler, a made-up ruler, that has as its units the length of the radius. and you have 1 radius, you have 2 radii, you have 3 radii. You make a ruler built off of the units of the radius. And adds a little flexible measuring tape and you wrap around. You guess where one of the radii is going to hit? At an angle of 1 radian. Guess where 2 radii is going to hit? At an angle of 2 radians. Guess where 3 radians are going to hit? Or 3 radii, I should say. At 3 radians. That's what pi really means. It's basically a ruler measured in the radii. There's 1 radius, 2 radii, that's the plural, 3 radii, etc. Why am I saying this? Because hopefully some of you have kind of learned about what 2 pi is and what pi is and how they correspond to degrees. Pi is 180 degrees. 2 pi is 360 degrees. Pi over 2 is 90 degrees. And some of you are like, yeah, they said that and I don't remember any of it. We'll go over it. But it's going to get even trickier when you get 1 radian, 2 radians. Like, I don't even know what those are. They don't have pi's in them. We have to think about it and say, well, what is 1 pi? 3.141596. So where would 3 radians be? A little bit before it. Where would 1 radian be? In the first quadrant. Where would 2 radians be? About 2/3 of the way through. And we'll keep talking about it. But my goal is to make the unit circle a little bit more understandable than it might have been in the past. So to help us with that, velocity, pi over 6, pi over 4, pi over 3. Some of you are like, oh, unit circle's coming. But not until next section. That's good. Unit circle's coming, but not until next section. So when measuring 1 full revolution of a circle, how many degrees is that? That one's easy. How many degrees? 360, right? But what is 360 degrees equivalent to?
2 pi.
Right? So we can say it's equivalent, kind of like 12 inches in 1 foot, or 60 minutes in 1 hour. Different numbers, but because of the units, equivalent measures. 1/2 revolution. That's like a semicircle, right? What would a semicircle be in degrees? I only had to go halfway around when I was measuring in order to get pi, or an approximation, 3.04. Kind of a lame approximation, but oh well. 1/4 of a revolution. 90 degrees, because there are 4 90s and 360. Or, see how I'm cutting in half and cutting in half, cutting in half and cutting in half? That's going to be 1/2 pi. But 1/2 pi is too hard to write, so we just write pi over 2. That's really just 1/2 pi, right? Here's the dealio, before we get much further. I need you guys to not think of pi as maybe you would think of pi. What? On Pi Day, question. How do nerdy people celebrate? They eat pie, but the problem is, if you think about a pie, what do you think about? A whole pie or a half pie?
Whole pi.
Oh. But does pi correspond to a whole circle? Struggle. Now, I could just say, okay, think about half pies, but that's confusing. Pi is half pi, it doesn't really make sense. Unless we started writing it out and we're like, oh, hey, pi is half a pie, and then now we have to spell everything out, and that's going to be annoying, right? So instead of thinking of pi as being a half pi, I'm going to say pi is equal to a calzone. What? Let's pretend we're in like New York or Chicago or something. If you say pi, they're not thinking, well, they might be thinking green calendars. They're probably thinking of what? Pizza pie, right? Now, very sad thing. Honors when we did this, over half the class said they never had a calzone. I don't know, but we'll vote. How many of you guys have ever seen or know what a calzone is? Okay, it's about half the class again. Are you guys serious? I don't understand. I'm really, yes, I am really. If you don't know what a calzone is, then how on earth can you actually relate with what I'm saying? This is so sad.
Did you even raise your hand?
I did. I thought about
Oh, this looks so good.
This is so sad, guys.
Oh.
What is a calzone? It's a pizza folded. And then like crunch. And then like baked.
Ricky,
So it's just goodness.
No.
Why am I saying pie is a calzone?
Oh, because it's half a pizza.
There we go.
I want one.
Does that make sense? Okay. So when you think about pie, you don't think about a Marie Callender's pie. You don't think about a whole pizza pie. You think about a calzone. Why am I saying that?
Certain pictures.
Because, you're welcome, nutrition is coming in a very long time. Okay, so, let's come back. I guess you could make it. You're supposed to fold it first and then bake it. And I was like, gooey goodness. Anyway, so, coming back. You can get you guys eating more Italian.
Oh, yeah.
Maybe Americanized Italian. Either way. New York Italian.
Not either way.
Chicago Italian. Okay, come back. The question. How many slices has my calzone been cut into? A 1, a 2, a 3, a 4, and a 5, and a 6, right? So when I get pi over 6, 1/6 of a calzone, it's kind of a small piece, right? So question, if I was to ask you something like, okay, where would 5 pi over 6 be? Pi is just a calzone. You have 5/6 of a calzone. Calzone is a semicircle, right? Where would that put you? How many slices do you have? Is that 5/6 of a calzone?
Yeah.
It's 5 out of 6 slices, right? So therefore, there's 5 pi over 6, and here's single pi over 6, right? And then you have everything in between. You have 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. Oh, some of those reduced. Oh, that's not too bad. Now, hold on. What if instead you cut your calzone into 4 pieces? You're only sharing for 4 people, or maybe you just, I don't know, don't want to eat the whole thing all at once.
It's like you don't want to
Looks more dainty if you eat it in pieces. Anyway. So 1/4 of the calzone would be pi over 4, right? Right here. So question, what if I was to go super crazy? What if I was to ask you to graph instead, where would 7 pi over 4 be? Oh man, that just got intense. 7 pi over 4, isn't that more than 1 whole calzone? It's almost 2 calzones.
Okay,
Think about the fraction, right? 7/4, what is that? 1 and 3/4. Yeah, someone took a pretty big bite, a 1/4 bite out of their second calzone. Where is this? Okay, hold on, focus. How many slices is that?
Where?
Now remember, anything unit circle is definitely not a calculator problem, so let's come back and focus. So we have 4 slices out of 4. We have 1 whole calzone, but we have to go get another 3/4, right? So I'm going to have to cut it in. There's 1, there's 2, there's 3, there's 4. I need to take 3 more slices. You see it? So we go 1, 2, 3, 4, 5, 6, 7, and then we end up right here. 7 pi over 4. Okay. It's 1 calzone. We have another 3/4 of another one. Okay, pi over 3. He's the biggest of the 3 slices, right? Maybe in color. He's 1/3. So if I was to have a lot of fun on this one, or if I was to give you something like, oh, I don't know. Let's do, let's go 4 pi over 3. Oh, that's too much fun. 4 pi over 3. What quadrant? What do you think? Why? Because you have a whole one, and how much more? Two fractions, right? Divide 4 by 3, there's another one left over, and 1/3. 1 and 1/3. So therefore, I have the whole calzone. I have all 3 slices, and then guess what? There's a second calzone. It's right below, and I have 1 more slice. So I have. If I can get my 1 more slice a little better. There we go. 4 pi over 3. How have you guys last year? Part of the trouble with the unit circle was just figuring out where the angle was supposed to be. Yeah, maybe calzones up. Maybe you need to eat some calzones to get inspiration for them to help. But either way. So what's going on in the bottom ones? Pi over 2, what's that? Half a calzone, right? What's pi? A whole calzone. Got it. What's 2 pi? Now I have 2 calzones, right? Make a whole piece of pie. Good stuff. So that's more exciting. Alright. Stuffed. Let's talk about about some special types of angles.
Pizza.
Remember, we're talking about angles. We're talking about what's radians, how do they work, where do the numbers come from, how do we think about going around the circle and like different types of radians, like pi over 6s and pi over 4s and pi over 3s and pi over 2s. You gotta think fractions. Don't be scared of fractions. Co-terminal angles. All right, my English nerds. Co, prefix, means what?
Together.
With or together, true?
Yeah.
Terminal, an airport? No. Ending, terminating. Ooh, nice, terminator. Oh, co-terminal, with or together. Terminal, now hold on. Can we go back really quickly to the very first thing that we wrote, and it was that little graphy thing? Guess what? One thing we didn't label. Every angle has an initial side and a terminal side. When we're putting an angle in an XY plane, in a Cartesian plane, in a coordinate axis, we have an initial side and we have a terminal side. We have a starting point and it rotates and then it ends, right? And technically, if you're thinking angles, they're technically rays, geometry, blah, blah, blah. Okay. We have an initial side, we have a terminal side. So when we come back and when we say, hey, this thing coterminal, what's it mean? Well, they're angles that end together. Huh? Share a, but angles don't have end points. What do they have? And sides, and the ending side is called the terminal side. Angles don't have ending points. Those are like line segments. Angles have ending rays, ending sides, and the ending one is called the terminal one. It's where it terminates, it's where it stops, right? Here's the tricky thing. We're going to come back and fill in that blank in just 1 second. So let me go ahead and start with, let's start with degrees. Degrees we're a little more familiar with. We'll do a radian one in just a second. Then we'll go ahead and make this one a little smaller, and then I'm going to go ahead and clone them that way. We can do one in degrees and one in radians. All right. Let's start with one in degrees. Let's do something easy, okay? How about 60 degrees? Sound good? That's probably a little bit high. That's more like that. Because 60 would be 1 or 2/3 of 90. So 1/3, 2/3, that's about it. 60 degrees. Sure. What's another way? You want to think about it? You can think about the angle. That terminal side is like the line of sight. You're facing due east. You twist towards due north, but you end 2/3 of the way there, and you're facing one direction. That could be your one direction. This line of sight could be the end of the angle. What's another way if you were twisting? What's another way that you could twist to get to that exact same location besides going straight there? Okay, you could go backwards. There it is, right? Mathematically, how do you go backwards? Going backwards.
Zoolander.
Yeah. Wherever we go. Come back. Well, you gotta say bye back. Come back. How do you turn the other way? Negative. You have to turn negative. But how do you turn negative? Well, think, guys, what would be the negative way of going to this angle? What measure would that be? Oh, well, the two add up to be what? 360. This and this is an entire revolution. So I need to turn everything of 360 except for 60. So what's that going to be? Aha. So one coterminal angle, let's name this angle theta. One coterminal angle could be alpha, and that would be negative 300 degrees, right? Now mathematically, how can we do that fast? 60 minus 2. Oh. You could turn the 60 and then subtract one full revolution. That's one way. What's another way of ending there without just turning straight there? 20 times. I might not demonstrate that. Let's just say 1 time. Okay, so go around 1 time, and then, oh, I have to go another 60, right? How do I mathematically go around 1 time and then go around 60? Say a whole 360 plus 60 more, right? So then the other way of doing it, here's my little alpha, this could be a little beta. My little beta could be 420, but mathematically, where does that 420 come from? Well, this one came from 60 minus 360, right? That's how we got the first one. U is a negative angle. This one came from 60 what? Plus 360. Question. Is there any way of ending at the exact same place without adding or subtracting a full multiple 360? If it was a partial 360, are you somewhere else? In order to get back to where you started, in a sense, you have to be a full revolution away. Whether you're going like turning positively, so turning counterclockwise, or turning clockwise, Whether you're turning positively or negatively, you have to be turning by full 360s. Otherwise, you're going to end up facing some other direction because you haven't gone a full revolution. Now, what if I gave you something like, let's do pi over 6. Oh, wait a minute. Why is pi over 6 a little one? He has a 6 in him, doesn't he? But he's only 1/6 the calzone. He's a little piece, right? Okay, so pi over 6. He's a little one. This got a little more complicated. Do I want to add 360 radii around the circle?
No.
I don't need 360. What do I need in order to get back to this position in radians? Yeah. A revolution in radians is 2 pi. So if I want to go ahead and say, do the negative one, I would say, hey, in radians, that should add up to 2 pi. So therefore, to find the coterminal in radians, I can just do 2 pi minus pi over 6. Aw, gross. That's not fun, right? Except, hold on. If you have 2 calzones, they're cut into 6. How many slices you got? 2 calzones, both of them are cut into 6s.
Whoa.
12, right? Because you have 6 for one calzone and 6 for another. You got 12. Can't we just get a quick common denominator and say, oh, that's just 12 pi over 6, take away 1 pi over 6, and you end up with what? Mm-hmm. Oh, wait a minute, but what direction were we going?
The other way.
Oh, so this needs to be a negative, right? This is one of those math times where you can be like, oh, but I need to be turning this way, that needs to be a negative number. To make it proper, actually this one should have been positive, and we should have subtracted the 2 pi. We actually kind of technically did it the wrong way. Pi over 6 is positive, 2 pi is negative. So the 12 pi is negative, the 1 pi is positive. Negative 11 pi over 6, that's one coterminal. But what's another way besides subtracting 2 pi? What else could I have done? Added 2 pi. So you can say, hey, beta is equal to pi over 6 plus 2 pi. Oh, don't even write it. How many slices? How many 6s? A 2. Do I have 2 whole ones?
12.
12 pi over 6. Maybe some quick fraction addition without maybe having to work quite so hard or be quite so terrified. Although like there are things much less fractions, so maybe we can fix them. But remember, the logical way doesn't work. You can always put the 2 pi over 1, right? Get the 6's and go ahead and multiply top by 6, multiply bottom by 6, and get your negative 12 pi over 6 and you go through. Okay. So, if you are in degrees, you have to add or subtract multiples of, but what if you're in radians instead? If you're in degrees, you're going to be adding or subtracting multiples of 360. Wait, multiples? Yeah, because you didn't just have to add one 360, you could have added two 360s, or 3 360s, or like Tyler said, 20 360s. I just wasn't really willing to. Do you want to make homework really hard or like a test really hard if I ask for a coterminal? You can like have tons of fun and waste tons of time and get one that's really far away and have to figure out if it's right or not. But yay! That whole wasting time isn't probably smart though. But at the very bottom of the page, definition, 2 angles. Ooh, what's that Greek letter?
Pi.
Not pi.
Sigma.
Phi. Phi, phi, fo, fum. Is it phi? Is it phi or phi? I think it's phi.
Yeah.
I saw the English one. Okay, so if I want a coterminal angle, I have to start with an original angle theta, and I need to either add multiples of 360. How do you show that in the formula? You put a little n I'll show you who n is in just a second. Or if I was in radians, I would start with an angle. 360 would not help me in radians. Remember, 360 doesn't really mean much. I mean, it means turning lots and lots and lots of times, so it doesn't really help me for the revolutions. And who on earth is n? Probably shouldn't do. It's in a set of integers. Remember, that means n is equal to negative or positive counting numbers. Because I need full revolutions. I need full sets of 360. 1 360, 2 360s, negative 1 360, negative 2 360s. I need full revolutions, otherwise I'm in trouble. Now I know time is almost done. We do have some other things we're going to talk about on Monday, like what's it mean to be complementary versus supplementary. Oh my goodness, more geometry.
No.
But then we'll also talk about converting and building bridges to get rid of what we don't want. All right, cool kids.
Why do we build
Homework, you might want to start.
To kill people, like Taylor.
But you don't have to. If you have your corrections, pass them straight back. Corrections, straight back. If you haven't already put them in the folder, if you're not distracted at the beginning of class. Corrections, straight back. People in the back, just leave them on your desk. I'll come by and get them. But they are due by the end of today.
I'm just don't get in the sand.
Any more questions? No.
Why do we build bridges?
You are what we don't want.
Oh, calculators.
So you're gonna build a bridge over me?
Yeah.
That sounds like a really bad idea.
Wait, so by building a bridge, we get rid of rivers. So you're telling me, Sean, if we build a bridge over a river, we get rid of what we don't want.